As usual, we start from reminding what happened last time. Last time was last week. We discussed scaling hypothesis about localization, actually, and the hypothesis is that the conductance of something depends on the size of the sample according to a universal law such that the derivative of conductance with respect to sign is the function of conductance itself. This is a hypothesis. It's not proven, but there are some evidence that it's correct. And we had this general plot how this function beta of g actually looks as a function of log g first. And we had three cases depending on the dimension of the system for d equal 3, d equal 2, and d equals 1. So for good metals, when g is large, it approaches the value d minus 2, dimension minus 2, so it's plus 1, 0, and minus 1. And when g is very small, it's called an insulator, then it's a linear function here. So this was discussed last time, and then we studied a two-dimensional case which approaches 0 in this limit. We studied quantum corrections, how this value deviates from 0 due to quantum effects. And I'm not sure, is it? I will try a different one, it's maybe better. So we studied a quantum correction to conductivity, quantum correction. So we have a classical conductivity, which is like a Drude or Einstein relation, and there is a correction due to quantum mechanics, delta sigma, which was due to this kind of fan-shaped diagrams with crossing lines. And we found that it is negative, minus e squared over 2 pi squared h times a logarithm of the size of the sample divided by the mean free path. So, and our conclusion was that this is for d equals 2 for a two-dimensional system. So our conclusion was that this function beta of g, for the second time, we draw it differently. We say beta of g here, but just g itself, not logarithm, on the horizontal axis. And the conclusion was that this quantum correction is negative somewhere here. It behaves like minus 1 over g. And this case, as I told you, is called the orthogonal case. Orthogonal. Then was another example, the same two-dimensional system, but with strong spin-orbit coupling. We didn't do any calculations explicitly, but we just counted how many spin projections there are, and we concluded that the correction is the same, but with an opposite sign, with plus. And there is an alternative curve that here goes like plus 1 over g, and this case is called symplectic. And in both cases, orthogonal symplectic, I will just put here spin symmetry is broken, spin broken, and orthogonal case is when spin is preserved. So there are two different cases. It's not a single function for everybody. There is at least one function for the case of preserved spin and one function for the case of broken spin. And in both of these cases, the correction is due to such a diagram. And we also discussed this diagram contains inside itself something that is called the Couperon, which is a ladder of retarded and advanced function pointing in the same direction. It's very similar to a diffusion, just the arrows point in the same direction, and it has a similar type of diffusion pole, dq squared minus I omega. There was some prefactor also here, so let me put it like this. It's a constant, a number with this denominator. And actually there is a third case which I didn't have time to mention. So this Couperon, the existence of such a mode with a pole inside, signifies that our system has some conserved quantity. Before, on the very first lecture, I told you that a diffusion has a pole because the total density is conserved. Conservation of total density in the diffusion equation leads to appearance of such a pole in the diffusion. Now, Couperon is a different object, and since we also have a pole here, it means we have some other conserved quantity. Well, actually, I don't know what this other conserved quantity is, but we have a certain symmetry that leads to existence of this dq squared minus I omega, and this symmetry is called time reversal symmetry. Time reversal symmetry. So time reversal symmetry means, as usual, that if you inverse the direction of time, everything remains the same. So if you take a diffusion, it has two arrows in the opposite direction, and then you reverse time in one of them, you can just flip this arrow. So if the symmetry is present, you have both a diffusion and a Couperon. Both things exist. So due to time reversal symmetry, we have this additional mode, and we have these quantum corrections. And there are two cases. If both time reversal symmetry is present and spin symmetry is present, we have the orthogonal case. If time reversal symmetry is present but spin symmetry is broken, then we have a symplectic case. And actually there is a third situation when time reversal symmetry is broken, which we did not discuss. If time reversal symmetry is broken, for example, if you apply magnetic field to a system, or if you have anything magnetic like some magnetic impurities inside it, they break time reversal symmetry, then this Couperon does not appear. Well, you still can compute such a ladder, but you will not have a singularity in it. So if time reversal symmetry is broken, this diagram here is zero. It just does not exist. And it means that there is a third case which goes somewhere in between these two, and it's called unitary case. Unitary case, time reversal symmetry broken. If time reversal symmetry is broken, there is a unitary case, and the beta function in this unitary case here is actually also negative, but it behaves as 1 over g squared. It's smaller, so this one is plus minus 1 over g is large, and this is minus 1 over g squared. So it also approaches 0 from below, but comes much closer to this 0. This result about the unitary symmetry and this correction we will derive at a later lecture. So I show it now, but later I will explain how this can be found. So this is more or less what happened on the last lecture. And we also had a million questions on the last lecture. They were all on the last lecture. I didn't say anything new so far, so nothing to ask about. Okay, if it's absolutely necessary, yes.
Maybe I'll try if you don't ask. So because there are these names, is there a relation between these names?
You will see it later. I mean, yes, there is an intuition, but it's quite indirect. So from this diagram, it's hard to explain. Okay, so what we are going to study today. This is a quantum correction to conductivity. Conductivity has a quantum correction. There is a very similar thing, which is a quantum correction to the diffusion constant, which is more or less the same diagram, but there are some tricks. And I will do this calculation today. We will once again derive the same result. I'm sorry. Maybe I shouldn't use this machinery. We will once again derive the same result, but from a different perspective. So this is also, again, a quantum correction. Quantum correction to diffusion. Correction to diffusion. So in the classical system, we have classical diffusion equation. Now we will have some corrections to it due to quantum mechanics. And as was discussed already on the first lecture, there is something called a diffuson, which depends on Q and omega, and which is due to this ladder diagram, almost like a Couperon, but with arrows pointing in the opposite directions, retarded, advanced, with the ladder of impurities. Now I will do this accurately with a prefactor. Prefactor is 1 over 2 pi nu tau squared dq squared minus I omega. And this object I will now call D with the index 0. This is a classical diffuson. And to this classical diffuson, we will have some quantum corrections. So quantum corrections are like this. The diffuson, which is without 0, will be just a pure diffuson. This is the 0 order approximation, plus correction will look like this. It's a longer ladder.
Should the outside points be connected together? Or?
If I connect them together, I will just have a different prefactor here. It's the same. I'm looking only at the pole.
I mean, like the total momentum from the left has to be the same as the one on the right.
Yes, this is true.
But there's 4 lengths here, so there would be 2 momentum, so you have 2 Qs on the left.
But this thing actually depends only on the difference of momentum. Okay, I can. You can say that you have momentum P on the upper branch and P plus Q here and just P here. And on the other, you will have some P prime plus Q and P prime. And the result actually does not depend on P or P prime. Yeah. Just because this first impurity line, it's a delta function, so this P will never enter inside. So the quantum correction will be the same type of fan-shaped diagram, this cross thing inserted inside the diffuson. This is a correction. But this is not everything. We should do something more. And we should add a diagram with two such things. And so on. So we can insert this fan 0 times, once, twice, 3 times, any number of times. We just have this single ladder and we insert this object any number of times. So I will write it like this. We have D0, the first term, plus D0 times gamma times another D0. Gamma is this object in the middle. Plus D0 gamma. As usual, we have a geometric series with all these things inserted. And if I sum up this geometric series, I will have the following thing: D0 inverse minus gamma and inverse once again. And I should write explicitly what gamma is, what is this single thing inserted. It has 4 green functions on the sides. I will draw it differently than it's here, but similar to how we did it last time. And then there is this long loop here with the ladder of impurities. So this object is called gamma. It has 4 points, 1, 2, 3, 4. And it's attached to 2 diffusons on the left and on the right with these 4 points. And inside it contains this fan shape, which I can redraw as this ribbon, this twisted ribbon. And this thing actually is a couperon. Yeah, the usual way how we do it. This is retarded and advanced thing, and yeah, they form a couperon. So we have to compute 2 things. We have to compute the couperon. Well, actually, we did already. It's up there.
This gamma you have to sum if you were to flip the 2 lines and have 1 inserted, 2 inserted, 3 inserted, and all of them.
Yeah. Yeah. So actually, I can write this thing as an integral, as we did it last time. The integral over some momentum q, which runs inside this loop. We have momentum q that goes along the couperon. And there are, oh, sorry, let me put a capital Q here, capital Q. And then there are 2 objects. One object is called H, and it depends on small q, capital Q, and omega. And the second object is the couperon, which depends on capital Q and omega, and that's it. So couperon is the ladder. It's what starts here and ends here. And H is these 4 green functions inside.
Sorry, could you draw momentums, how they come to the diagram, because it's not so clear where Q, and is it really a couperon? So
Okay, so
from the momentum point of view.
if you have a couperon, just a ladder, you have steps like this. And in each step, you have momentum P plus Q on the upper line and momentum minus P on the lower line, such that the total momentum that propagates, the sum of them, equals Q. Then I say there is a momentum P running in the loop, so we integrate it out. We have something which is function of only Q, and then we sum up the ladder. This is what happens inside the couperon. And what happens inside this thing, I will draw in a minute. I'm just saying H is these 4 green functions, and C is the couperon, and here in the loop we have a capital Q going, we have an integral of this one, and we have a small q coming inside here and going out here. It's the same q which we have inside the diffusion, inside this ladder. Yep.
Just the difference in this line below, on the bottom, if we put arrow to the previous side and have p. So, because I thought if arrow to the right side, it should be only positive p. But
No, p is a vector. It can point in any direction, so there's no notion of positive p. It's a vector. They are all vectors. Energies are fixed. Each line has the fixed energy, and the difference is omega. So this is epsilon, this is epsilon, this is epsilon plus omega, this is epsilon.
Okay, so also you should technically be 4 vector.
Yeah, very technically, yes. So for the main object here actually is this H thing. It has a name. It's called Hikami box. Hikami box. Hikami is a proper name of a Japanese physicist, Satoshi Hikami, who invented this thing in the year 1980, plus or minus. So, H. Now I will write it explicitly what it is. It's the product of 4 green functions, 1, 2, 3, 4, with arrows like this. 2 of them are retarded, 2 of them are advanced. And as I already indicated there, we have momentum q entering from one side and exiting here, and we have momentum capital Q going like this. And we can assign all momenta now to all the green functions. For example, let's say this one, this retarded function, will have momentum p. Then this advanced function will have momentum p minus q, such that q exits here. Then this retarded function will have momentum minus p minus small q plus capital Q. So when I sum up 2 momenta here, sorry, it's plus small q. Yeah, when I sum this plus this, I will have just capital Q. And then here, I will have minus p plus q.
Here, these lines should all be full Green's functions, right?
Average green functions. Yeah, and this thing inside this loop, as I do usually, I will say that momentum p goes inside the loop, it is integrated out. This p which enters in every green function. And then there are some corrections, smaller capital Q, that shift it a little bit. And the result of this integration will be a function of these 2 momenta. So, what is this? Let's compute it. It's easy, right? We have an integral nu dig psi. Psi corresponds to the momentum p, the one that circulates here. And then we have 4 green functions. And just for simplicity, I will neglect capital Q and small q. They are small momenta. P is large moment. P is like Fermi momentum. These are some small additions to it. Let's neglect. So we just have 2 retarded functions of p, 2 advanced functions of p. We have epsilon minus psi squared plus 1 over, we did this already a few times, 4 tau squared and once again squared. And this thing is 4 pi nu tau cube. It's just a number. And this is extremely bad. This just doesn't correspond to any known physical principle, because if we have gamma added here, which is a number, it means it will be added for the diffusion, it will be added to the denominator, and it will kill the diffusion pole. It's no longer zero when Q and omega are zero. The number of particles is not conserved anymore. So, sorry, this is bullshit. This cannot be correct. This cannot be correct. Something is missing. And actually, that's why this thing is called Hikami box, because Hikami found out what is missing. Yeah, so now the correct answer, I will bring back a different board, because I will need some more space. Oh, no, it's still too high. So, Hikami box, in a correct way, is this diagram with 4 green functions, retarded, advanced, plus I will now, since Hikami is Japanese, I will write vertically, plus one other diagram, which is retarded, advanced, with one extra impurity line inserted this way. And I'm no longer Japanese, so I will write horizontally, plus another diagram which has a dashed line inserted this way. So if you add up 1, 2, 3, then this will be the correct Hikami box.
So only 3 are needed?
Only 3.
Okay.
Yeah.
Why are you not connecting lines?
What do you mean connecting lines?
Hikami diagrams, this function will be connected to a point between.
Because this is where I will connect a couperon, and this is where I will connect a diffusion. They are not at the same point. It's, yeah. It's all covered, but yeah, the diffusion is a ladder. It has 2 lines, and they are connected here.
Yeah, but what is the diagram? Because I thought it's like part of the big diagram. It's not a part of the component.
You have a diffusion with 2 lines, and then you attach a Hikami box like this. For example, this crossed one, and then you attach a couperon here, and you continue a diffusion here with all the ladders.
So
And all green functions are connected.
we are not happy because there's no need for a further infinity.
Yep.
How I can see these diagrams from gamma?
Okay, if you look, this is a diffusion, again, a ladder. It starts with a ladder here, and it continues with another ladder. Then you have this fan shape in the middle, which is a couperon. And this diagram corresponds to Hikami box, which is just 4 green functions. They're here, 1, 2, 3, 4.
This crossing part corresponds to gamma.
To couperon. This crossing part is a couperon.
Equals gamma.
This crossing part is a couperon. These 4 green functions form a Hikami box, and they together form gamma. Now, if you take your Hikami box and you cross, and you insert this line between 2 retarded functions, remember this line is retarded, this one below is advanced, it's like adding another dashed line over here, which connects 2 retarded functions in gamma.
Why can't insert a diffusion inside this
Inside what?
These two Hikane boxes instead of just one crossing line.
You mean a ladder like this? Because they're both retarded. Diffusion needs one retarded and one advanced.
Okay, so and if both retarded, it will be zero because the integral.
If you have, yeah, if you insert a second line, then this integral between the two lines will be immediately zero.
Okay, yeah, because both.
Yep.
Hey, can I ask something? So,
Yeah, yeah.
is there an intuitive way to see why this should be the correct?
Well, in some sense,
Or did this?
in some sense, we understand this is correct, right?
Yeah. Okay.
And then Hikami realized that if he adds one line here, this line does not cross anything else, so it should be added. We add as long as we don't introduce more crossings.
I mean, this is technically like a four-point function.
Yeah, and this one also. But if you insert both this and this, you will introduce an extra crossing, which is not allowed.
Oh, right. You still have that crossing.
Yeah.
So it just means that we lost it in previous one, right?
That we what?
When we get the gamma, it's bullshit. So
Yeah.
we just, these two guys was like kind of lost.
These two were not included. That's why we got the wrong result.
Is it correct that previously we expected this like thick line, let's say, the function line already includes all the bones, like all the impurities inside?
You mean
I mean, all,
self-energy for single green functions?
yeah, I mean all this function already should
Yes,
include
yes.
this,
They
because they're all like inside already.
Yeah, this is correct.
In this tower.
Yeah,
In this
yeah.
tower thing. Why it is not included already this
Because this one is not a self-energy. Inside it has lines that connect to a different green function. So it's not one particle irreducible. If I cut these two lines, it will not separate. It will still hang on to the other line.
These are all skeleton
But
lines.
still, we can add such lines on the parts where it's just vertical impurity lines. Like it's still.
I
mean, imagine
Do not
you-
understand, sorry.
Imagine you drew the same line, but in the region they are only vertical lines.
You can add in diffusion.
Oh, I see. You are saying that I
mean,
can
while
I can do it like this.
While deriving Cooperon and Diffusion, we already knew that this line is somehow included in that. I mean, and then we calculated it separately.
Wait.
Diffusion itself and Cooperon itself.
Wait. Sorry. We have first self-energies for single particle green functions, which are already included in each line here. We have 1/tau as an imaginary part. Then we compute a ladder with two green functions and we add vertical lines just because they do not cross each other. This is the only way to add lines without crossing them. And this is a pure diffusion, classical. Now we add something which includes crossing of lines. For example, we take this ladder and say, let's cross two lines like this. That's all, very nice. But then it turns out that if we add more lines in this fan, they are all of the same order. It doesn't matter if we cross 2 or 3 or 5 or 55. So we need to sum up this whole thing. And then Hikami comes and tells us that if you also add a line above or a line below, it is still a diagram with just a single crossing, so you should also include that one. That's all?
In what sense single crossing?
Maybe you should go below.
I'm sorry.
Oh, yeah.
In this sense, this ladder has a single crossing here, and if you add an extra line, it will not introduce more crossings. So we
So that's why we
flip this ribbon, so now we count such crossings.
then calculating just simple diffusion, it will cause crossing if we.
Yeah.
Okay, and why while calculating just simply Cooperon, we didn't add something like that?
Because we never computed quantum corrections to Cooperon. we compute quantum corrections to diffusion. We have a diffusion equation with this diffusion, and we want quantum corrections to the diffusion. So I have to bring the board back. Yeah.
Sorry, what about the line that you have raised? What if you draw? You just raised the line which connects
This one.
two parts. No. On the diagram, yeah. If you will connect 2 points on the upper grade function, which intersect with the vertical dashed line. What will happen?
Just a moment. So you mean if I do like this,
Let's say yes.
This
you introduce an extra crossing, this is next order correction.
And what will happen if you do the same but on the diffusion lines, which is just
Here,
vertical? Yeah.
this is also an extra crossing which you introduced, so it's a part of the next gamma. I mean,
But it doesn't look worse than just the tutor. It looks the same order correction, just
yeah, but we insert this gamma, this thing, we insert once, twice, 3 times, 4 times. So insert it once, twice.
gamma, right?
Yeah, it's included.
wait,
It's not so.
I don't know, is it included? Oh yeah, it is. 'Cause
It is.
You can have just
It is.
one line.
Yeah, yeah, yeah.
You can have just one input.
It is included. This one, I mean, with the cover, this one is not included.
Will include all possible one crossings.
So understand correct that if you have these 2 rainbows which have a cross, it's going to be next order.
Which to this rainbow,
Yeah, and if you add another one,
where?
up
Here?
here, yeah, you add
You mean if I add another line like this,
like this here, it's going to be next order.
it's going to be 0. Actually, because you have a loop with only retarded functions. You have a loop with only 2 retarded functions. It's the same as I explained here. If you cross it twice, you get 0.
So then you need what? At least 3.
No. Well, actually, the trick is there are several things you should. You can add as many lines as you like, but if you have some integral over momentum which involves only retarded functions, it will be 0.
Do tadpoles come up here ever? Or
Tadpoles?
tadpoles?
No.
Or do you need to introduce interaction?
No. With the disorder, you never have tadpoles
Okay.
because it's an extra green function.
Yeah,
So
like a
so
class.
you start with 2 green functions, you add impurities which are just crossings, and then you connect them in all possible ways. You cannot introduce a new green function which wasn't there originally.
Oh yeah, it's always 0. 'Cause
Yeah. Okay, so may I continue, please? Great. As was written just behind this part of the board, this diagram here equals this one here, the first one, 4 pi nu tau cube. But, as I explained, it's not correct. We have to add these other 2 diagrams here. And these other 2 diagrams, well, first of all, they are equal, actually. You can compute one of them and then multiply by 2. They just so happen to be equal to minus 4 pi nu tau cube together. So when you add all 3 diagrams, you have 0.
But here you have the same assumptions that Q and BQ is 0.
Yeah. So 0, I mean this one plus this one is 0. It means we should compute them a bit more accurately. Namely, we should take into account these small momenta that were shown on the other board. And we do it in a standard way as we did when we computed a diffusion, for example. We expand in powers of this small thing. And we have some series expansion here, 1 plus some small numbers. Remember, we had this letter B, the object with 2 green functions. So that had 2 green functions. Now this has 4 green functions, but it's a very similar calculation. So you have for green functions, you expand in powers of small momentum difference. And I did this at home, so I can immediately show you the result. It's actually 1 minus tau dq squared minus tau d capital Q squared plus 3 times I omega tau. As usual, as we did with B, up to linear order in omega, up to quadratic order in momentum. The same as in the diffuse zone. Sorry? Small q comes from here and exits here. Capital Q goes this way. Yep.
A little bit lost. So we are doing the same perturbation theory for quantum field theory formulas for
We never had any quantum field theory so far.
I mean, Green's function.
Green's functions are inverse Hamiltonians. They are operators, no field theory.
So in quantum field theory they used to. So
I refuse to do any quantum field theory.
no, but that's like perturbation theory, no?
Perturbation theory is
Scattering.
for scattering,
Yes.
has nothing to do with quantum fields.
You don't need QFTs.
Exactly.
You
But
don't
okay, anyway,
you
it's
don't
not
need
my
QFTs
question.
because there's no interaction between particles.
There is scattering. There is
Yeah, but it's a single
I'm sorry, we can discuss this. So the other two diagrams, they are the same number times -1. And again, there are corrections, and they are 2 tau dq squared plus 2 tau d capital Q squared and minus 4 times I omega tau. This line is that one, these two give this one. So the first term, 1 minus 1, they cancel. And if we add up them everything together, we will have the true Hikami box, now the correct one, which is, who can do this math? What is 2 minus 1? Is 1. What is 3 minus 4 is also 1, right? Great. So it's 4 pi nu tau squared, nu tau cube, 2 minus 1, yeah, dq squared plus d capital Q squared, and 3 minus 4 minus I omega. Right?
This is the hard part.
Yeah. This one I didn't do at home. So, sorry? Yes. You see, I got a mistake. Tau power 4. So now we will take this H and put it here. I can remove this one. This is wrong. I mean, the answer is wrong. The correct one is up there. Okay, so we have an integral. Now let's do it 2 dimensions, as usual, 2 dimensions. So this capital Q is 2-dimensional, which means Q dq over 2 pi. Hikami box, 4 pi nu tau 4, 4 pi nu tau 4, divided the couperon, where is my couperon? It's gone.
Sorry, is that exact? They're e squared over 2 pi squared.
E squared where?
They're quantum correction.
No, that's for conductivity.
Okay.
I need just a couperon, and the couperon has 2 pi nu tau squared in the denominator. And then I have d small q squared plus d capital Q squared minus I omega divided by d capital Q squared minus I omega from the Couperon. Couperon, this one, has momentum capital Q.
So the Couperon is the same as.
It's just this.
It's classical.
It's just this ladder. Yeah, it's the same.
Okay.
It's the same up to the coefficient here. So this fraction that I have, I can take an advantage of having a whiteboard, so I can erase things, and you have to write them again, if anybody is writing. So d small q squared divided by d capital Q squared minus I omega plus 1. And this is still some bullshit, but already better. What happens if small q is 0? If small q is 0, this term disappears, 1 remains, some number, infinitely large actually, yeah. We still have a problem because we add something in the denominator which is a constant, which is finite and even infinite, not 0, when q and omega are 0. So what should we do?
That's hard, no? If it's so infinite, is it finite large, then put it into the diffusion and
In the denominator,
yeah, so it's just 0. It's not
So diffusion does not exist anymore, it's 0. Diffusion is never happening.
But you accepted that into D we're not supposed to get that.
Oh, that's a good point,
So it's
yeah.
like, oh,
Well, this way I have just proven that you don't have metals in any dimension.
yeah. I mean, it's not that bad.
Yeah.
We need to include all possible lines, parallel lines.
Yeah. Actually, this is a good point. So, what is our gamma? What is this object that we are calculating? It's a piece of the ladder which starts with 4 green functions and then contains either one crossing or 2 crossings, or it can also contain, say, a crossing with 1 line on top, which is due to this diagram with this cancelled Hamming box. Now the question, what will happen if I take for the Hamming box the first diagram, which is just 4 green functions, and for the Couperon, which I insert inside here, I will take a ladder with just 1 dashed line. I have 4 functions, and I insert a Couperon which contains only 1 dashed line. How will this diagram look like? No. Couperon dashed lines connect retarded to advanced.
It's like
Like,
accelerated.
it will look like the line we drew before in diffusion.
It will look like this. Yeah, this is gamma, these 4 lines. Then I have my Couperon, which is this thing. And then I have a single dashed line. So if I unfold this ribbon back, it's the same as just doing this thing.
So we have to really have to subtract one.
We have to subtract this thing. We have to subtract the thing when Couperon has only 1 line and is equal to 1 over 2 pi nu tau. And the Hamming box has only the empty part and is equal to what I just erased, 4 pi nu tau cube. Which means we should subtract this unit.
We overcounted these diagrams.
Yeah.
Can I try to ask again the question that I tried to ask before? Because I'm still confused.
Yeah. Yeah.
So we're dealing with perturbation theory, right? So
Right.
it's not clear until which order we are dealing with perturbation theory, because with some summation. Can I finish this? Now we say that, okay, we use diagrammic technique, and up to unknown order we have expression in terms of diagrams, and now we are confused for a long time which exactly diagrams should be, because this diagram doesn't work, that diagram doesn't work. Maybe we can just go back to perturbation theory, not in the scope of diagrammatic approach, but the scope of just expressions, see exactly which expression we have up to each order, and don't bother with like summation to infinite order, and just up to second order obtain finally some correction, be happy with the result.
Very good question, but it was already answered on the lecture number 1. We first start with drawing all diagrams, all. We do perturbation theory to all orders. We are attempting to solve the problem exactly. And then, by analyzing these infinitely many diagrams, we find that whenever we cross impurity lines, we have some extra smallness, from which we actually understood what is the parameter, what is the small parameter of our expansion. Small parameter associated with every crossing is K Fermi times L or E Fermi times tau, well, actually a large parameter. And then we say, okay, let's sum up all the diagrams which do not have these crossings. They are all of the same order. You cannot just take the second order or the third order. You should add all of them. They are all of the same order, as long as they do not contain any crossings. We did this, we find the classical result, the diffusion and the Einstein relation. Now we are doing quantum corrections, so we include diagrams which have only one crossing and see what corrections they produce.
So previously we have found the quantum corrections. So
To conductivity. And now we are computing quantum correction to the diffusion propagator. This is a different object. It also has quantum corrections.
what is the order until which
We insert just the first order. We have classical result plus first order quantum correction. Nothing more so far. And this is it. We have cancelled our spurious number 1 here. Now this object goes to 0 when Q goes to 0, exactly as it should be to conserve the number of particles. And who can do the integrals? I cannot. It's 2 tau squared, right? 2 tau squared divided by 2 pi dq squared, diffusion constant cancels, right? Small q squared times the logarithm of capital Q of L divided by L with a minus. No, why with a minus? With a plus. It's this thing. So I'm saying that this is a logarithmic integral, and Q, the upper limit, is inverse mean free path. And the lower limit, actually, I don't need it. I can use frequency to cut it from below, but I prefer to put frequency to 0 and instead to do it by system size, the infrared curve. So if I do this and frequency is 0, then I have just a logarithm of the ratio of these two with this prefactor. Now, what happens with my diffusion? This is my diffusion. Diffusion is this thing. So let's write it. We have diffusion inverse, 2 pi nu tau squared dq squared minus I omega. And here I should add minus gamma, minus this. Minus tau squared divided by what? By pi, right? By pi q squared logarithm L over L. And then this whole thing is inverse once again. So what I get is 1 over.
You should put omega to 0.
Here.
Calculated gamma
No, I don't have to. Oh, now imagine omega is finite. It will enter here and also under the logarithm.
I mean, it seems that you should calculate gamma also until the first order.
If I calculate gamma, taking omega into account, it will just replace L under the logarithm.
Okay.
So if you like, I can write L which depends on omega. L depends on omega. 2 pi nu tau squared times. So I have two terms with q squared. One is d q squared, and the other one is 2 pi nu, 2 pi squared. Something is missing as usual. Or maybe not. Minus tau squared, 2 pi squared nu minus logarithm L over L divided by 2 pi squared nu, and this whole thing times q squared. So, what we have just found, quantum correction to diffusion, means that the diffusion constant acquires a quantum correction and is replaced by diffusion constant minus, plus some delta d, some correction, and this correction delta d equals minus log L over L divided by 2 pi squared nu. Do you have a question about this equation? Okay, please.
So, because you said 7 minutes ago that we're now doing quantum correction to diffusion, now we know quantum correction to conductivity, we know Einstein's relations, so maybe we can use just
This is a good point. I will answer right now. Conductivity, according to the Einstein relation, is E squared nu times d, right? So, since our diffusion constant acquires a correction, it should also lead, according to this identity, to correction to conductivity, which is E squared times nu times delta d, which is, if I take delta d from here and put it in here, minus E squared over 2 pi squared log L over L, which is exactly the correct thing written on the very top of this board. Now I can use a special device. This one. So,
because when you stated the problem, like 10 minutes ago, I made this thought like this, so I'm surprised that we are told doing a lot of complicated diagrams.
we do it not only because we don't know the answer, but actually I can tell you that this answer is not immediately obvious because conductivity is a product of nu and d. And we can also have correction to conductivity due to corrections to the density of states.
In our model, we don't.
How do you know this?
I mean, on which point we could say that density of state will change?
On which point can you say that diffusion constant has changed?
Well, diffusion constants because of scatterings, and we take into account second order of scatterings. Right?
Diffusion constant.
So we are looking more exactly how scattering happens. That's why diffusion will change with conductivity.
If we survive a bit longer during this course, you will see an example when density of states also has corrections. So it is not completely obvious from the very beginning that it's the same thing. And second, it was very important to understand how this quantum correction works for the diffusion ladder, for the diffusion propagator, because we will use it later. And as a byproduct, we have just checked that Einstein relation remains correct even when quantum corrections are taken into account. So somebody asked me on the very first lecture, what happens with these quantum corrections? Do they break? Do they alter this? I guess it was you. Do they alter this identity D equals V Fermi squared tau over D? So this is what they do. They change diffusion constant, they add something to it. But actually you can, my answer that time was wrong. You can trace it even further back and you say it's a correction to tau, not to D. So D is V Fermi squared tau over 2 for 2 dimensions. And this delta D actually is a correction to tau inside.
So I have a question about this correction is independent of both scales, right?
Oh, you mean this scales here?
Yeah. Or
No, actually it mainly depends on the infrared scale. So look, it's a tricky thing. The diffusion is a function of Q. So strictly speaking, you should replace L here, the infrared scale, with something that is related to this Q. And when Q goes to 0, this thing will diverge.
okay, that's true. But like I'm trying to say, like this is technically a measurable thing. Like you can't really distinguish, experimentally speaking, you can't really distinguish the quantum correction or.
Oh, no, of course, only the sum is measurable. You cannot, or you can, look, no, you still can separate them if you, sorry, as I say, if you break time reversal symmetry, the Couperon propagator becomes gapped. So if you break time reversal symmetry, you remove this correction. So you can measure how this D or how the conductivity depends, say, on magnetic field, which breaks time reversal symmetry, then you will directly measure this thing. Sorry. So what I also wanted to say is that this whole thing is just like many equations, some integrals, we calculate something. I will now present some pictorial explanation what all these quantum corrections do without any equations, which I already did last time, but half an hour after the lecture was finished, so not everybody have seen it. Yes, if it is short.
It's very short. So we learned this very complicated theory about the summations coming box, but we got result which we could write in one line after known result from previous lecture. So this peak theory, is it used somewhere?
It is used in the next lecture, if I am still alive by then. I do this on purpose, because later I will present even more complicated theory and understanding of it, which is more general, which includes many more things, but understanding of this requires that you understand this calculation. That's it. Of course, if you just need this correction or the correction to conductivity, it was already last time, you don't need anything else. Sorry.
Very short.
No, for now it's enough. Let's wait 10 minutes, then you can ask the next question. Yeah, so I would like to present some qualitative explanation of what this quantum correction actually does. And to do this, I will draw the same diagrams, but in real space rather than in momentum representation. And I will literally draw them. They will not know integrals, just the pictures. So what do we know about green functions in real space representation? A green function is this object, yeah, is the line with two ends, and it decays as the distance between these ends divided by mean free path, the average green function, sorry. The true green function does not decay, but the average does. It's the same, we discussed this previously as a function of time, we had t divided by 2 tau. So it's the same thing in real space. So whenever I draw a ladder, the diffusion is a ladder. It means that I have some set of impurities. These are my impurities, just points. And I have an electron that goes and scatters on these impurities in some random way. And this is a retarded function, retarded. It represents a quantum amplitude from going from this point to this point. I can draw many trajectories. Each trajectory contributes to the total amplitude. Now, for the diffusion, I have a second line, which is advanced and which goes through the same impurities, but in the reverse order with the arrow pointing in the opposite direction. So it's this thing, it scatters on the same impurities, goes in the opposite order with the advanced function. What does it mean? Between any two impurities, I have this pair retarded advanced, which is just the classical probability. It's the square of the amplitude. Advanced function is the complex conjugate to the retarded, so the product of them is just the square modulus of the amplitude. It's a classical probability to go from here to here, then to here, then to there, then to there, so on. That's why this is a classical diffusion. It just counts how my particle moves around, scattering on the impurities, and computes the total probability to go from this point to that point. Now imagine, in this picture, I will try to insert a quantum correction. I have this diagram with a fan shape. And one other thing. Each step of this ladder is quite small, quite short in real space because green functions decay. But by adding these steps, I can make my particle go as far as I like, from this end to that end, because diffusion does not stop after going to the mean-free path scale. So that's why I need a ladder to make my diffusion propagate to some long distances, longer than this one. So now, what will happen if I insert here a fan shape? Let's look at the diagram. This is my diagram. This is where my diffusion ends. And then here in between, I have a fan shape. So I have some last impurity before, let's say it will be this one, and the first impurity after, it will be this one, and between these two impurities, I should insert this thing. No problem. So I remove this leg with two lines and replace it with something else. I add 3 more impurities, 1, 2, 3, that form the fan shape here. And I say my retarded function is scattered. This is impurity number 1, 2, 3. This is retarded function. This is impurities 1, 2, 3. My retarded function goes and scatters 1, 2, 3, and then goes back to the usual track. But my advanced function scatters on the same 3 impurities in the opposite order. So it goes from here, from this impurity, first to impurity number 3, then 2, then 1, and then here. That's it. This is a Couperon, these 3 impurities and the 2 legs between them. Now, look, this is retarded function. This is retarded function here. This is retarded function here. Advanced function goes like this. Advanced function, advanced function, advanced function, and advanced function here. Yeah, so this is a Couperon. Here, advanced and retarded have arrows in the same direction between these 3 impurities. And this thing in the middle, between these 4 impurities, I have these 4 green functions. This is the Hikane box, this part with this butterfly thing. And actually, each step in this picture is very short in real space. It cannot be longer than the mean-free path. So this is a ladder, this is like a snake with many, 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 many very short segments. This is also a snake with very, very many short segments. And this couperon thing is also a long line with many segments. And this Hikami box is a small box. It's like mean-free path in size. So this is a bit misleading. I will redraw because I can erase.
Can you calculate again couperon part?
Which part?
Thank you.
What I'm saying is that this couperon can go very, 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 very large with many steps like this. But Hikami box is small.
Can I ask again?
Yes,
This big circle, it's couperon or?
it's a couperon, yeah. And this is a couperon loop, which is inserted more or less at a single point inside the diffusion propagator.
Basically, you perform all possible transpositions of slopes of two paths.
Yeah, actually, that's the reason why I prefer drawing diagrams in this form, because here you see this Hikami box is a compact object, and this ribbon I can draw as long as I like. Yeah, so what does this quantum correction actually do? It does the following thing. It tells us that the total probability to go from point A to point B, probability to go from point A to point B, equals sum over all trajectories. We have many trajectories going from here to here, which scatter in different order on different impurities. We have an amplitude of each trajectory. Let's say t is a trajectory, and we have an amplitude which is a function of t. We should sum up all these amplitudes. And then we should take this sum and take the absolute value squared. This is the probability. We compute the total amplitude for something, and then we square it, and we get a probability. Now, what happens if our system is almost classical, classical physics almost works? It means that all these amplitudes are very rapidly oscillating functions. You shift one point by just one, whatever, wavelength, and the amplitude already changes sign. So it's a very, very fastly oscillating thing. So you approximately replace this sum squared by the sum of amplitude squared. This replacement means quasi-classical approximation. You have the sum, which is squared. You can expand the brackets, and you have one amplitude times any other amplitude, the sum of all possible products, and you keep only those terms that are squares of a single amplitude, because this square is a real number. It does not oscillate, so it's not so much sensitive to shifting some small details. And yeah, and the quantum correction is then everything that you're missing from this thing. It's the sum over two trajectories, T1, T2, with amplitude of T1 times amplitude of T2, complex conjugate. As I said, in the classical limit, this thing oscillates violently, so you don't really need it. But if you take two trajectories here, T1 and T2, which are almost the same, they have this loop inside, which is the same for both trajectories, but they traverse this loop in two opposite directions, it turns out that all the phases the electron acquires along this loop cancel out in this product, because retarded times advanced, because the couperon is a nice object. The green function does not depend on the orientation of the arrow. When the two arrows are in the same direction inside the couperon, this oscillating amplitudes also cancel out. The only thing which does not cancel out here is inside the Hikami box. So in Hikami box you have these 4 lines that are not very well synchronized. That's why inside the Hikami box we have a small parameter. This is where our lines cross. This is where we get a small parameter. That's why this is a small correction to the classical diffusion. And yeah, that's all about this particular topic.
Is Hikami box also suppressed when you break time reversal symmetry?
No, Hikami box is not.
Second to the correction with the two Hikami boxes, diffusion will work. And
Yes. Yes. So, for example, a good question. As I said, if the time reversal symmetry is broken, couperons do not exist and we do not have this quantum correction. How does it happen? If you apply magnetic field to your system, you break time reversal symmetry. I apply magnetic field like this through the board. I have these 2 trajectories, one with a retarded function, one with advanced, going around the loop. And before, they had perfectly the same amplitude. But now, if I have some magnetic flux inside this loop, and they go in the opposite directions, they acquire some extra phase due to magnetic flux, and it breaks the interference. So actually the contribution of this loop gets smaller. This magnetic field suppresses it. That's how you can kill the correction and how it's actually measured experimentally. You measure how conductivity depends on magnetic field at very low temperatures, 2-dimensional sample, and you have this logarithmic dependence on magnetic field, which is called negative magnetoresistance usually. This is how it was first observed. Okay, so let's move on. We actually very much behind the schedule. I planned to be at this point in the end of the 2nd lecture, and now it's the end of the 4th lecture already. No. I will answer all the questions afterwards, right? So let's at least start a new topic today. This was the yesterday's topic. And I hope we do have like half an hour yet to work. So the new topic today will be very much new. And now, only now, we will have some quantum field theory. For the same phenomena, the electrons in the potential of impurities in some disorder, propagation of electrons in a disordered medium, we will build a proper field theory description. Is this online? No. So the new topic has a name. It's called non-linear sigma model. Each word has no meaning so far. What is nonlinear? What is sigma? It's just some 3 random words. So what have we learned about disordered systems? Individual green functions for single electrons, on average, decay in real space. They cannot propagate. After the first scattering, it's already gone. What can propagate are these special things that are diffusons and couperons. Some correlator of 2 particles, they can really diffuse to a long distance because we can build this ladder and overcome the suppression. So there is a very specific theory which operates not in terms of electrons, but in terms of these diffusons and couperons. They are like primary particles in that theory. It tells how these diffusons and couperons propagate, how they interact with each other, how they scatter one on the other. And effectively, if you build such a theory, you will understand not only this lowest order quantum correction, but you can do it more or less to any order. And one of the people who did this was actually Hikami. What he said is, this box, he didn't call it by his own name. This box is actually a vertex how diffuson and couperon interact. We have diffuson attached to left and right, and the couperon attached to up and down. So actually it's like diffuson comes, couperon comes, they interact, and then they go away. So this Hikami box is the interaction vertex. And then there is a whole field theory that is in terms of these diffusons and couperons, and which has these Hikami boxes as interaction vertices. But we will come to this point much, much later. First, we will derive this effective model, and it will take the rest of today's lecture and the whole next lecture. Hopefully, we will be done by then. So, first of all, question to everybody in the audience. Does everybody know what a Grassmann variable is? Okay, it's very unfortunate because I was about to use this thing quite much. So, very, 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 very brief overview without going into any details. Grassmann variables, or Grassmann whatever, Grassmann variable is an object. It's like a number, but taken from a very special mathematical algebra. It's like numbers, but when you multiply them, they anti-commute. If you multiply AB, it's the same as minus BA. There are some strange numbers that change sign every time you interchange the order of multiplication. So Grassmann variables anti-commute. They appear in physics quite often because they are Grassmann variables. They are eigenvalues of creation and annihilation operators. If you have operators A and A dagger, which create or destroy a boson, the eigenvalue is the usual number. And if you have creation and annihilation operator for the fermion, the eigenvalue is the Grassmann number. Because the operators anti-commute, so the eigenvalue should also anti-commute. That's how it works. So if you have any Grassmann number and you square it, you immediately get 0. You can also add two Grassmann numbers. You can multiply Grassmann numbers by ordinary numbers, like double them or take a half of it. It doesn't matter. It's just like this. And finally, what you can also do, you can differentiate in a Grassmann number and you can integrate in a Grassmann number. It's very easy. It's much easier than in usual numbers. For example, if you have a function of x, alpha, and beta. Alpha and beta are Grassmann numbers. X is a usual number. So these are Grassmann. First of all, since any Grassmann number squared is immediately 0, this means you can expand this function in a series, assuming alpha and beta are small, and this series will end just at linear order. You cannot go further than linear order because you will get all zeros. So it's like f0 of x plus f1 of x times alpha plus f2 of x times beta plus some f3 of x times alpha beta times the product. And that's it. It should be linear in every variable. You cannot have it to the power more than 1. But you can have a product of them. And then this thing, this f1 of x, is actually the derivative of f with respect to alpha, because you take alpha out. This is how you do the expansion in a series. You take a derivative, and this thing is the derivative of f with respect to beta, and this one is the second derivative with respect to alpha and beta. I am omitting a lot of details here because the derivative in alpha is itself an operator that anti-commutes with another derivative. So the derivative in alpha beta is minus the derivative in beta and then alpha. So it's not clear in which order I apply this thing. It's just to give you some taste of how things work.
Why df over the alpha is not f1 plus beta over f3? Because I thought it's the usual way how you write. Okay, good.
And what concerns integration, that's even easier than this. When you have an integral of such a function, you want to integrate over alpha, the function that depends on x, alpha, and beta. What you do, you actually replace this function by this expansion. It's the same thing, yeah. And you need to know just two rules, two simple rules. If you have an integral of some Grassmann variable of a constant, it's obvious, yeah, what could be an integral of a constant? Of course, it's 0. And if you have an integral over any Grassmann variable of the variable itself, this is 1. That's all. So you just take this expansion, insert it here, and you say all terms, this term and this term, they do not contain alpha. So the integral of them is 0. And these two terms, they do contain alpha, here and here. So the integral d alpha times alpha is 1. So the answer is f1 of x plus f3 of x times beta. There are no limits when you integrate over Grassmann variables. Okay. It's just a definition, yes.
But if you will integrate over beta, you will have f1 minus f, right?
The same integral over beta of f equals f2 minus f3 times alpha. Minus, because I have to interchange alpha and beta before I can use the identity that the integral is 1. And interchanging will change the sign. And if I have an integral over both variables alpha and beta of f, I will apparently get minus f3. So variables anti-commute, derivatives anti-commute, and also this d alpha d beta into the integral, they also anti-commute. Which is what is even worse with derivatives. There is since the operator d alpha is Grassmann itself, it may be important whether you differentiate from the left or from the right. If you multiply with this operator from the left, or if you do it from the right, it may be two different operators.
Minus most equation also you should change.
Yes. Okay, so this is almost all you need to know about Grassmann variables. One last thing you should know about any variables is how to compute Gaussian integral. Gaussian integral, I will have exactly three examples. Example number 1. You have an integral over some usual numbers, let's call them, I don't know, b. But we have many of them. B is has an index, it's like 1, 2, 3, 4, some number. B is a vector, just a column of many numbers. And then I have a Gaussian integral, exponent minus B transposed times matrix A times B. What's this integral? Who knows? We have some quadratic form. B is a vector, A is a matrix.
1 over square root of determinant.
It's right. It's 1 over the square root of the determinant of A.
Wait, here B is a normal number?
Yes. And, well, there is also some number like pi to some power, which is whatever, pi to power n over 2, where n is the number of these things, because each eigenvalue gives us the Poisson integral, which is the square root of pi. Second example, I do the same integration over the vector b, but now it's a complex vector, and I will write it as the integral over b star and b of the same object minus b now dagger a b. What's that? Now it's 1 over determinant, right? It's just 1 over determinant a, also pi to some unknown number. Now the question. This is wrong. Do you know that this is wrong?
If A is invertible?
A should be a symmetric matrix. A is symmetric, but because, you see, if A is not symmetric, then you will get a square root of determinant, but not of A, but only of its symmetric part. Because only symmetric part of A enters here. If you transpose this number, A is replaced by A transpose, and it's all the same, so only the symmetric part enters. So this is actually this is the correct answer for any matrix A. This is only for symmetric, that one for any. But this one is correct for any. There's no symmetry requirement for this integral. And finally, I said it will be 3 examples. I'm sorry, it will be 4 examples. Example number 3. We have a set of Grassmann variables, alpha. They also form a vector. And I have an exponent minus alpha transpose A alpha. A quadratic form in Grassmann variables in the exponent.
The square root of determinant is 0.
It will be the square root of the determinant, that's right. So what is the difference? With Grassmann variables, it doesn't go to the denominator, it goes to the numerator. It will be a square root of determinant of the antisymmetric part of A. Because alpha and alpha anticommute, only the antisymmetric part of A enters here, and it will be a square root of determinant. You can check it, this is a very simple thing, just take a 2 by 2 matrix. It will be only 2 Grassmann variables. It's very easy to do this calculation explicitly. If you have a matrix A, which is A, B, C, D, put it here, and your answer will be B minus C. Because you take only antisymmetric part. Antisymmetric part contains B minus C over 2, C minus B over 2. Then determinant is their product, the square root is their square root, so the answer will be B minus C over 2. Yeah. Never mind, that's an easy thing. So the 4th example, just like here, you have 2 different Grassmann variables, alpha and beta, 2 vectors with Grassmann variables, and you compute, say, alpha times A times beta. Alpha is a row, beta is a column. So this is like a matrix element, it's a number. And then this thing, I will put alpha transpose just so that you know that it's a row. So then the answer is the determinant of A without any restrictions. Sorry, I have not yet finished. So this is very important, but it will not be important for my lectures, but this is a very important mathematical object. If you imagine that A is antisymmetric, just let's say A is antisymmetric, then I don't need to do this. I mean, I can just say square root of determinant of A, right? But what happens if I flip the sign, if A changes sign? Then the whole integral should change sign. So actually, when you take an antisymmetric matrix and you compute its determinant, explicitly just say you have matrix elements A, B, C, D, like this, any matrix but antisymmetric. You take a determinant, you have a huge polynomial in all these letters. They are multiplied in different orders and add up. There is a mathematical theorem that this polynomial for an antisymmetric matrix is a total square. And you can take a square root by just removing this total square. So this is also a polynomial of the matrix elements of A. And you will get this polynomial if you do the integral. And this polynomial has a name. It's called Pfaffian of A, which we will never use in these lectures. It's just a fancy thing. Okay, what's your question? This is usual variable, this is Grassmann variable. You see, this is a Latin letter and this is a Greek letter. That's the difference. The same. These are two Grassmann variables.
A is arbitrary.
Yeah, A here is arbitrary. Okay, so we will need to know how to compute these Gaussian integrals and nothing else about Grassmann variables. So let's at least start doing some nonlinear sigma model. I will just remove this whole garbage. So when you build a field theory means you replace your particles with the fields. You have a field which has a value at every point, and the amplitude of this field is more or less like saying this is the amplitude to find a particle at this point. So if you have electrons, you have a field which represents these electrons. The larger is your field here, the more is the amplitude to find the electron here. And the square of this field is it's like a wave function. The problem with electrons is that they are fermions. That's why the fields that represent them should be Grassmann valued fields. So we have a metal with electrons inside, and we introduce Grassmann valued with a hyphen field. And we call it phi. What is field? What is the difference between just Grassmann variable and Grassmann field? Field depends on point in space. That's it. It's a Grassmann variable, a different Grassmann variable assigned to every point in space. It's a function that takes Grassmann values. Now, I will actually do a bit more, since we usually have retarded and advanced functions in our diagrams. I will introduce not a single Grassmann valued field. I will introduce two of them, one retarded and one advanced. So it will be fields in plural. And the fields will be phi with an extra index R or A. Two fields. one retarded, one advanced. And once again, there are field theories with fields that are real fields and that are complex fields. For usual bosons, yeah, this is like a complex number and this is like a real number. But for Grassmann variables, there is no notion of complex conjugation. So you just can say, I have two different Grassmann variables and I can call them conjugate to each other, or I can call them just independent variables. It's the same. This star just means a different number. But actually, it's quite convenient to say that this is a complex Grassmann valued field, which means we have two fields instead of one. We have field phi and the field phi star. So we have this and we have phi star retarded advanced of R. So actually we will have four of them. Two retarded and two advanced.
But this is just notation.
Yeah. I can call them phi 1, 2, 3, 4. Or I can use different letters. Phi, chi, psi, omega, whatever. Just four fields.
Like retarded and advanced correspond to like electrons and holes?
No. They actually, you will see. It's just.
Because usually for electrons they just take one field, right? And then it's complex one. So two fields.
Yeah.
You have double that.
So I will arrange these fields into a vector. Just two components. I will just write phi, meaning I have a column which has retarded phi and advanced phi, like this. And they both depend on R. I mean, this depends on R and this depends on R. This is a column field. And I will introduce another one and I will call it phi dagger. And this will be a row and it will contain the complex conjugate fields. So how do we go from this to this? We transpose and complex conjugate, right? Of course, we get two unrelated fields, but who cares? It's just a notation. And dagger is a very nice notation because it operates exactly as it would operate in usual numbers. So these are my fields. They are arranged in these two things. One is the row, the other one is a column. Both are functions of R. And now I will introduce something which is called the action of my field theory. And the action is the following object. Minus I integral over all positions in space, phi dagger of R, and then some operator here, and then phi of R. And the operator is epsilon minus psi of P minus V of R plus omega over 2 plus I0 times lambda. This is a very, very, very important equation. So I have to also put a box around. So this is an operator. This is actually my Hamiltonian for electrons. Yeah, it's the kinetic energy, it's potential energy. This is just a parameter, it's a number, which is the energy. This is something which will be called frequency. It's the frequency that, for example, we had in the diffusion, omega. And this lambda is a matrix. It's a 2 by 2 matrix, which has a very simple form. It takes the value 1 for retarded fields and minus 1 for advanced fields. So it's called the matrix in the retarded advanced space, in this two-component space where I have my vectors. So it's just a diagonal matrix. I have this whole operator. It's a diagonal thing. I have something in the upper corner and something in the lower corner. And both of them look like the green function, but it's slightly different energy, one with added omega over 2, the other one with subtracted omega over 2, and one with plus A0, the other one with minus A0. So actually what I have here in the square brackets is a matrix. This square brackets is a matrix which has epsilon plus omega over 2 minus the Hamiltonian plus I0 inverse. This is what stays in the retarded block. And here I have epsilon minus omega over 2, minus h minus I0. Well, it's not inverse, sorry. It's not yet inversed. Yeah, this is my matrix. So this is like the inverse retarded function, and this is like the inverse advanced function, which are taken at two different energies.
I have two questions. So
Yep.
these fields, are they defined only over space or space and time?
Only space.
Then I have another question.
Yeah.
So epsilon and omega.
Are just numbers.
So epsilon, they're just numbers, but how do we have a physical interpretation, or will we tell what it is?
Yeah, epsilon is the Fermi energy.
And omega.
Since, simple explanation, usually when you have a field theory action, you have fields that depend on time, and instead of epsilon, you have d by d time.
Yeah.
That's because you study, usually, interacting particles that can change their energy during the interaction. We study just a single electron that scatters on impurities elastically. It never changes its energy. So we can take that action, convert it into a Fourier transform to energy representation. Instead of time integral, you will have an energy integral here. But then you say every energy is independent, so let's study just one of them.
But then omega is something else, right?
No, omega is also a number. We just would like to study a diffusion, for example. Diffusion depends on omega.
So omega is then a parameter.
Yeah, it's just a parameter, which is, you will see, it's quite natural. It will appear quite natural. So what can we do with this action? This is just a quadratic expression in these fields phi. It's phi dagger, and some huge matrix in between, even infinitely large, because each point in space is like a matrix index. And this integral over R means take a trace. And this operator, actually, it's almost diagonal. This V of R is diagonal. These numbers, they are all diagonal. Psi of P has a derivative. P is d by dr. But once you take a derivative, you still take both things at the same point. So it's like slightly off diagonal, very slightly. It's almost a diagonal matrix. So what will happen if I, for some stupid reason, compute an integral over all my fields, phi star and phi, of the exponent with minus the action. Action depends on phi star and phi. Who can tell me what the result will be? I formulated the question clearly, right? What is this integral? It's this one. It's this one. It's the determinant of this square bracket matrix. Actually, I have some random signs. I have minus here, and I have minus I there. So it's a determinant times one of them. But actually, this object has a name. It's called Z, and this is called a partition function. It's just that determinant, right? But I will not use it, at least not now. This is a partition function of my field theory. It's a very, very basic, simple. it's time independent, it's quadratic, there's no interaction, nothing, it's just pure Gaussian integral.
In principle, you can calculate.
Yes, in principle you can. Now, a different question, this is Z. A different question, what will happen if I take the same integral, phi star and phi? Yeah, when I write this capital differential, it means path integral, which just means integrate over phi at every point. Phi is a different variable at every point r, and I integrate over this variable at every point. This is a path integral. So if I have this exponential of s, but in addition, I will add two fields. Phi retarded taken at point r, and phi star retarded taken at point r prime, and then exponent of minus s. This is also a Gaussian integral, but it has not only this quadratic thing in the exponent, it has also some quadratic thing in the pre-exponent. This thing is also known. It's not in this list of examples, but it's quite easy to derive. And actually, it equals to z itself. Yeah, it's almost like that integral, z itself, times something extra. And this something extra is the retarded green function taken between points r and r prime at energy epsilon plus omega over 2, and with a number that I do not remember. Minus I. Minus I. Because here is minus I. Yeah, it's just the matrix element of this matrix inverted. You take the matrix, you invert it, Gaussian integral does it for you. But actually, this exact identity is usually written differently. It will be right now the same identity, but I will take this z and put it in the left-hand side. Or probably it should have been I and not minus I. It's like this. It's minus I divided by z. Yeah, now it's correct. So it's minus I here, also minus in the exponent. That's all. So the green function can be very easily the exact green function without any averaging. The exact electron green function in a given potential V of r without any averaging can be represented as such a Gaussian integral. And the fields here are exactly the fields that know what point is the r, which point is r prime, and which function I need. It's retarded. If I want an advanced function instead, I will put two advanced fields here. I will get a advanced function here, and it will be at energy epsilon minus omega over 2. And that's it. So I'm not sure if I should.
Yeah, here the border matters, okay. So because the stars on the right have an additional minus, okay.
Yeah.
Because usually the stars go to the left, then it's just IG.
Yeah, maybe.
If you will take one retarded point, what you will have anything?
0.
And then it's zero inverted.
But it's diagonal matrix. If you invert a diagonal matrix, then off diagonal elements are 0. Okay, I'll do the very last thing. I have 3 minutes left. The very last thing. Why do we need this? Well, we need these green functions. Yeah, we want to average them over disorder. But we can't because we have this z here. So green function depends on the external potential, on V. How? We have V buried somewhere inside this action here. But also we have v buried somewhere inside the z because z itself was the integral with the same action. So we have, it's like a fraction. This is a numerator, this is a denominator. Z is the denominator, and we would like to average it over all possible realizations of v, but we don't know how to average a fraction when v enters both numerator, in the numerator and in the denominator. So, to overcome this problem, some smart people have invented a smart way to do this, and this smart way is called replica trick. Actually, they have invented a few ways to do it, and replica trick is just one of them, but it's the simplest one. The others are trickier than this. Replica trick. Instead of one disordered system, one piece of metal with this Hamiltonian, we take n identical replicas, identical copies of this system, identical copies, which are also known as replicas. So instead of one piece of metal, we have 10 identical pieces of metal. 1, 2, 3, 4, 10. They are so much identical that this function v of r is the same in every of them. Just exactly the same. All impurities are staying exactly in the same positions with exactly the same potential. And we do this whole calculation. We just have like a stack of this n copies, and we now say this stack of n copies is all. This is the whole sample that we study. So our Hamiltonian will be an operator in this space of n copies. Our fields will be fields not only in real space, but also in space of these copies. Everything will be multiplied by n. So we have phi, our fields, phi, which were retarded or advanced, and with a star or without a star, they depended on r. Now they also have an index I. And this I goes from 1 to n and counts these copies. And this matrix here, so I will just have it right here. I will say phi I, sum over I. I have I identical actions. All these things are the same. They do not depend on I. Is it? The total partition function, z, which is this integral here, is now a product of n identical integrals. Yeah, because we have them all we have the sum in the exponential, so we have a product, and each integral over each phi is independent. So z is replaced by the same z to power n. The total partition function is raised to power n. And for the green function, I will use a trick. I will say I need the two fields here, retarded and advanced, in points r and r prime, in the replica number 1. So I'm asking what is the green function in the first copy. I have n copies. I measure something in the first copy. The other copies are just staying behind. So I have z power n here. And this thing is the same green function I had initially. I take this integral in the replica number 1, but in the replica number 2, 3, 4, and so on, I don't have this prefactor, so they just produce extra copies of z, which cancel extra copies of z here, and I, in the end, have just 1 over z.
So you have to raise n.
Hmm?
You have to raise n. Right?
No. These differentials, they involve all fields within all replicas, but this one is only from the replica number 1. So, okay, this is z of 1, just one copy. There's this z of 1 copy. So what I will do now, this is still an identity, nothing changed. It's just I multiply it with n minus 1 copies of z and divided it by n minus 1 copies of z. Just the same object. But now I can do a trick. This right-hand side here, this one, does not depend on the number of replicas. Yeah, I cancelled all of them except one. So since it does not depend on the number of replicas, nothing will change if I take this number to 0. Who cares? For each n, it's the same number. N equals 1, 2, 3, 4, 5, 6, 7, all the same number. So for 0, it's the same number. Nice. And now, when you take a limit of the product of two things, you can take the limit of each of them, right? In most cases. So what's the limit of z power n when n goes to 0? 1, exactly. So I can erase it. And minus I can also take out. That's it. The green function in a disordered system can be written as this Gaussian integral when I have n copies of my system. Here I take the fields only from the copy number 1, from replica number 1, but I do the integration with over n copies, and then I take the limit n to 0. And this is my green function. This is a replica trick. And this is very nice because now I can average over disorder, because the only place where my disorder still remains is here inside this action, but nowhere else. I get rid of this 1 over z here. This is the end of today's lecture. Thank you. Well, first, yes, we work at 0 temperature, and second, this is actually not so important because we work at a fixed energy. Whenever you solve the problem with a given energy, you can restore any result at finite temperature by integration with a distribution function. You have a distribution function which tells us we have electrons at this energy with this probability and at that energy with that probability. So if you know the contribution of a single energy, you can then integrate over the whole distribution and you will get a result at finite temperature.
How is that z to the n and so on?
Yeah, it's limit of any number to power n when n goes to 0 equals 1. This is the basic identity. Yep. Oh, how many do you like?
I don't know why you choose 4. It's 4.
Just because I want two green functions, retarded and advanced.